Hello, my friends, data scientists, machine learning engineers, and learners. After last lesson of a complete machine learning procedure, today I am going to show you how valid machine learning predictions are. I am going to explain the details of how valid are the predictions made by machine learning, especially in the context of macroeconomics. So let's go ahead and start the process now. Here I have under cell 1 I have importations. I imported pandas, numpy, seaborn, matplotlib, and styling ggplot, and then I have a data in my C drive, which Excel file, which I read here. Since the data was without the title, so I added the header equals none. That is appropriate when there are no titles in the data. And then I gave the name of the heading of each column. I gave the name like country, population, GDP, happiness, democracy, inequality, like that. This is a model that is trying to make predictions on the basis of the model. The model here is we are going to predict the GDP of each nation on the basis of predictors. The predictors here are happiness, democracy, and inequality. And these predictors, being of different scale, like inequality ranging from 0 to 1, democracy ranging from 10 to 100, and happiness similarly ranging from 1 to 8. Different scales. So to standardize them in a standard scale, the next aspect what I did is here, I standardize them. I standardize by using x minus x bar divided by sigma, standard deviation. Here, x is the column name minus the mean of the column divided by the standard deviation of the column. Okay, that is a standard method of standardizing. Now, as a result, we can tell that a standard unit change in predictor causes this percentage change in the response variable. That is very comparable and a robust method for scaling into standard units. Excuse me. As a result, you can see here, okay, the population and GDP we did not standardize, and you can clearly see they are right skewed, okay, skewed to the right in there, because you can see the data nature. There are nations with 600,000 population to the nations with 1,463 million people. So in such a vast differences, is obvious, natural to see the rightward skewness. More people are towards the left in smaller areas, and large are in a few outliers are in the right side. That is all it says. But when we standardized the scale of standard happiness, democracy, and inequality, you can see approximately normally distributed in all three levels. You can see that. Okay, so that is the background of that. With that, and we read the data, and you can see here I invoke the tail, I can see the 5 last rows. Here, Mauritania, population 5.32 million, GDP 11.95 million, happiness index of 4.51, democracy 1.04, inequality 32. Inequality is measured by Gini coefficient, okay? Gini coefficient data is available. Similarly, Albania, Suriname, Greece, Uruguay, all these methods we have. And when we standardize, you can see standard happiness minus 0.84 because it will fall between 0 and 1. Remember, the mean equals 0 and deviation equals 1 of a normally distributed standard normal distribution. Okay, so similarly here you can see standardized democracy, standardized inequality. So we have done this standardization, and I want to show you before we run the regression, let me show you the correlation coefficient to gauge which variables are strongly correlated, which are not, and that will give us a clue of which variables we should keep and which variable we should not keep, and which variable should be the response variable, the target variable. Okay, so for that I am going to run this plt dot figure fig size equals, let me write just fig size equals 18 and 7. I want to make it a wide so that it is visible. And SNS dot heat map, it takes selected calls, we have selected columns, dot core, we want to see the correlation matrix, that's why I'm doing. Instead of making a table, I am going to see all these correlation coefficients in a heat map. Okay, not equals true, and CMAP equals cool warm, just to give some background. Cool warm center equals 0 so that the numbers are centered. And format, we need format so that the correlation numbers are not in several decimals places. Okay, 0.2f, so they will be in 2 decimal places. All right, so now what we're going to do is, let me give the correlation coefficient bar as well, so that darker color bar shows stronger correlation and lighter lower correlation. Okay, C bar underscore KWS equals, let's make it a label. Label is going to be correlation coefficient. Okay, that will be the C bar. Make sure you are seeing it. PLT dot title, just let's give a title. The title is going to be, let me make this correlation map of selected column. Those are the numerical columns, okay, because correlation need numerical columns. All right, let me make it a little bigger. Font size equals 18, comma, font weight equals bold. Okay, just to distinguish the title. All right, plt.show. Okay, so that is this. Let's run this and we will see. I need to refresh the column because in the top cell. Okay, here you can see. Now you can clearly see correlation map of selected columns. Okay, so the first thing to do here is where are the strong correlation, which variables are strongly correlated. I can see the strongest by looking at the darkness of the color. Okay, so the darkness here, this on the diagonal, you can see this is 1. Obviously, it is going to be 1 with itself. Population with population will be 1. GDP with GDP will be 1. So ignore those and then look at the dark colors. So what's the biggest dark here? 60.60. In my judgment, any correlation above 0.6, 6 or above has a strong correlations. So here, happiness, standardized happiness with standardized democracy has strong correlationship. So by this, we can infer that they might be creating multicollinearity problems. So hence, we can use one and ignore the other as a predictor. Okay. Similarly, next, what is the next large number? The next large number I see is 0.55. So what is this? Population correlated with GDP size as 0.55. That means that we cannot ignore population as a predictor variable if we want to predict the GDP. So that also gives us a cue. So after examining this, we can see that we can go ahead and run a regular OLS methods and later and regular OLS methods and then check the validation. Okay, carry out the validation of that model in making the predictions. Excuse me. So let's go ahead and do that. So how am I going to do that? Import stats models dot formula dot API as SMF. Okay, and formula equals, so here we're going to start that. So GDP will be the target, and we are going to predict that on the basis of population plus STDARDIZED happiness plus STDARDIZED inequality, because we will drop democracy because they have a strong correlation which will cause multicollinearity. So inequality. Okay, so on the basis of these three predictor, we are going to target the GDP for making predictions. Let me make sure I have this GDP is also correct. GDP, see here, I was making error here. GDP, G is cap. GDP. Okay, so once we have written the formula, now regression, reg equals smf.ols formula, comma, data equals named df, okay, dot fit. All right. So I want to make sure you are seeing this. I'm sorry for if it is not visible. Fit. Now print regression results. Want to show that in the next line. Okay. And let's display that. Display reg.summary. Okay. So let's look at the results and then we will go for validating the predictions of these results. Okay. Let me make it. All right. Hopefully that will be it. Yes, that was it. So you can see here, this model has been able to produce the results. The R-squared value, the explanatory power of the model is 0.35, a modest explanatory power, but R-squared is not be all and all powerful thing. In prediction, we will look at the validation of this model, how close they are from the actual in making the prediction, okay, on average, how off they are of the actual GDP. Okay, so the only thing that I always like to look at these model is that the sign of the coefficients, okay, and the significance. You see, standardized inequality is not significant at 5% level of alpha, and other variables are significant. And population, larger the population, obviously GDP is going to be larger, which you can see significant here. Okay, for an additional 1 million population, you can see an increase of 10 billion GDP. Similarly, happiness is the biggest contributor. For since we had standardized the happiness, we can say that for one additional standardized increase in happiness, 871 billion GDP increases. Okay. Similarly here, for an additional standardized increase in inequality, 253 billion income increases, which is perverse. It should be increase in inequality should decrease the GDP. But you know, in many countries, larger economy like the USA has one of the highest inequality in, but it has the largest GDP. So you can understand that. Okay, so those I'm not going to go in detail. Excuse me. For our purposes, what we need to look is skewness and kurtosis. You can see clearly we have extreme skewness to the right, and extreme outliers, many outliers. Look at these values, 62.477. Kurtosis does not give us the direction, but it gives us the outliers. Okay, and the residuals, these are residual measures. Okay, the residuals, standard error of summation of standard errors are skewed Okay, similarly, if you look at jerk vera number, just the raw number itself tells you that there is a lot of residuals that are skewed and heteroscedasticity problem, a lot, no homogeneity in there. Okay, that's all we're going to say in this, and the next part is going to be validation of this model, followed by we'll scale the skewness by log transformations and see that how much the skewness and kurtosis have been smoothened. And with after log transformation, we will also carry out the validation of that model and compare with this regular model with log transform model. That will be next. Okay, so wait for that. Thank you. After our foray with running regular ordinary least squares regression, let's straight go into the validation of the model for prediction purposes. So for that, first we will predict and then we'll go for validation of those results. Okay, so from sklearn dot linear model import linear regression, make sure no typo. Okay, and once we import the linear regression, now let's define x equals named df. We're going to pick up the predictors, and those were population, comma, standardize, st DARDIZED, happiness, comma, STDARDIZED, inequality. Okay, so make sure I am writing these correctly. Standardize, population, STDARDIZED, happiness, STDAR. Okay, so those will be our predictors, and the target is going to be y equals named df is going to be GDP. Okay, that once we specify that, so what is model is going to be linear regression that we imported. Okay, that we imported, and model that fit what we're going to fit x versus x and y. Okay, this is the model that we fit, and now let's make y prediction. Ypred, name it ypred, equals model that predict what we're going to predict, x. Okay, model that predictor, the predictors are x. Okay, so to display that, to show that in a tabular form, I have made this table form equals pd.data frame. Okay, just don't want you be not seeing this, so I'm trying to be as careful as I can. Okay, that is going to be the first thing in the list is going to be country. Okay, and that country is going to be named df. Let's access the column country. What is the country? It is a string str dot capitalize. It will be nice to show the first letter of each country in capitals. That's all, nothing necessary. You can just skip that if you don't want. And here going to be actual value of those. What is actual? Actual is y. And we're going to do predicted. What is going to be predicted? Y pred. Okay, comma. And I would also like to show you each individual nations, the variation, the error between actual and predicted for each nation, which will not really be a validating the model as such, because that will come with mean absolute error, percentage, root mean square error, but it will give us an idea of how much error we have for each nation. The magnitude error per nation, that is what it will give. Okay, this is not a measure on the basis of which we are validating the overall precision of the model. Okay, this is just a measure the extent of error for each nation. Okay, so for that we're going to do 100. We're going to give in percentage. That's why 100 here. Y pred, oh, excuse me, y pred minus y pred minus y, okay, divide by y. You know, this is new minus old, the difference divided by the old. Okay, y pred y. So that will give us the error percent for each nation that we want to see. So to see that, let's give all nations equals table form that sort values. We will sort by this. This is sorting by actual values. Okay, sort value with actual, and display round. I'm just using round to make sure that we don't get those many decimal places and which are hard to read. Round to. Okay, so this should give us the error for each nation. Let me run it and we'll see about it. Excuse me, name df is not defined. That usually means I need to rerun the kernel. Okay, here you can see here for each nation we have the prediction, and you can read this here. Gambia actual was 2.7 billion, predicted was minus 313 billion, which is absurd. Predicted negative, and this is a huge error percentage, 31,400% error. Similarly, Suriname 4.5 billion, predicted 921.57 billion, So, obviously it overestimated, overpredicted, and 92,056.62% error. Eswatini, another nation with 5.2 billion actual GDP, it predicted minus 529.67 billion. It's absurd, predicted negative, and error percentage is 53,067. So another nation is Laos, a actual GDP of 17.25 billion. It predicted a GDP of Laos should be 193.25, over predicted, that is 19,224. So you can read all of these, you can see all this in the list, and then you can read. So it shows that there are large errors. Error percentage is really, really large by this model, which is not surprising because the countries are so much diverse. There are so many outliers. Like United States is clearly an outlier. 30 million, 30 trillion. And these nations, some of these are 2 billion. So obviously many outliers, and hence you see the error percentage so large. What is more instructive and important is the model prediction via the model prediction capacity using the mean absolute error, root mean squared error, root mean squared error percentage, all that. Okay, so for that, let's go ahead and do into that. I am going to just write here model validation parameters. Okay, so let me just write r square equals this. Just I am showing the r square, nothing else, just to see if it is same as we got in the regression or no. R square times score. Okay, so you see I got squiggly because I forgot to import from sklearn dot matrix import mean absolute error, comma, mean absolute percentage error, MAPE, mean absolute percent error, percentage error, root, no, mean squared error, and r squared score. You see now my squiggly is gone. Okay, r2 score, y comma y pred. Okay, next let's just print r squared. Okay, I am going to show r squared in round r squared in 3 decimal spaces. Okay, that is that. Let me keep going and then we'll pause because the lessons are really long, but for the sake of completeness I have to go through this each one. Okay, this is what the teacher does, not just pick and choose a few. A complete solution. Mean absolute error, oh, error, let's make it y comma y pred and store that in MAE. Okay, mean absolute error gives you on average how much the model is off in predicting. Okay, ignoring the signs. Mean absolute error y pred. And less before that, better measure is MAPE, MAPE, mean absolute percentage error. Okay, so how are we going to get that? Mean absolute, we already imported above, percentage error. Okay, mean absolute, oh, above, so see typo, mean absolute percentage error. Okay, and that will be y comma y pred, okay, times 100. We're going to show in percentage terms, so times 100. Okay, now let me print that now. Print mean absolute percentage error. ERROR error. MAPE. Okay, is going to be round. When you do percentage, you round into 2. MAPE 2. Okay, so let me run this and I would like to explain this. After that, I will come for the root mean square error. Okay. Okay, now you can see R squared 354 exactly matches mean absolute percentage. So it tells us how much off we are from the actual. We are off by 1116.85%. A very, very large percentage off from the mean value of prediction. From the actual value of prediction, we are 1116.85% off from that. So nowhere near the actual prediction. Really, really far off statistics. Okay, model is absolutely not adoptable for this. So regular OLS model is absolutely not adoptable. Okay, so before I move on to the other model, let me just do this also. Show you mean MSE, mean standard error, equals mean squared error I am doing this to show that RMSE, root mean squared error, is a true measure that measures the distance in Euclidean norm method from the actual, how far it is. If we take a straight route to the point, between one point to the other, it gives you the distance, how far off it is in square root terms. That's why I am getting this. RMSE equals np.sqrt MSE. Okay, and the better measure to to see that is in root mean square percentage error. Okay, so for that RMPSE, root mean square percentage error, equals np dot sqrt np dot mean, okay, y minus ypred divide by y times raised to the power 2 square root, right, raised to the power 2 and by 100 times 100 times 100. Okay, that will give us root mean square percentage error. So let's print it. Print root mean square percentage error is going to be root mean square percentage error is going to be round RMPSE, 2, because it is a percentage. Okay, so let's look at this. See here, the percentage error, if directly going from one point to other, from actual to predicted, in square root terms, percentage is 2992.02. This also confirms that the model, the regular linear regression model, is erroneous for making predictions of this kind. So what were the causes of this? You can see the outliers by looking at the value of kurtosis. You can see the skewness by looking at the distribution diagrams above, all these things. So this begs us that we need to scale down the outliers that we are seeing using the log model, log transformation model, that will smoothen the skewness and kurtosis variables. That will be next in this lesson. That will be next step. So wait for that. Thank you. Now that I have shown you how erroneous linear model is in making predictions, in this lesson as well as immediately previous lessons, that linear model is erroneous in making predictions, especially with the data that we have, where we have these extreme values, a lot of outliers from small to the very large. In this situation, linear model is not appropriate. So to solving that problem, let's see how log model helps. Okay, we're going to start log model to solve the suitability problem created by the linear model. So let's start with log GDP equals np dot log named. We're going to access the GDP that we want to log. Okay, and formula equals, now here we're going to do log GDP as the target, log GDP with population. Make sure I'm sensitive to the casing. Population plus stand STDARDIZED happiness plus STDARDIZED inequality. exactly the same model. We just have log model. We are logging the target. Okay, so log regression, log reg equals smf.ols formula, comma, data equals named df dot fit. Okay, dot fit. Now print, just being consistent, print log regression result. Okay, so here display round, no round, display log reg dot summary. So this will show us the results. Without going in much details, I am going to just explain a few points, look at the skewness and kurtosis values, and then straight go into the validation, which is the purpose of our lesson today, right? Let's go ahead. There should be error because NP is not run all. Let me make sure it is running all. Need to be, yeah. So far, so good. Okay. See now, the results are, look, it improved the R square from 35% to 51%. So that's not the main point I want to explain. Here, I want to explain that, look at the coefficients now come to the correct form. Standardized inequality is negatively associated with GDP growth, which is the correct diagnostics. And skewness kurtosis, look now. Look how that little act decreased the skewness minus 0.295, which means leftward skewness a little bit, small skewness to the left, and kurtosis is leptokurtic. It is only off by 0.265. See, the kurtosis raw value around 3 is considered good, so this is off by that. So this has improved the model tremendously. Okay, it has improved the model tremendously. Now, we are going to not stay with the glory of that model. Our purpose is to validate the model. Okay, so prediction and validation, model validation, TION, log model. Okay, so let's go on that one. And so for that, we're going to do log y equals log GDP. Okay, log y equals log GDP, log model equals linear regression. The library is the same, scikit-learn. Linear regression, log model dot fit x, comma, log y. Okay, and we fit the model. Now let's predict it. Log y pred equals log model dot predict. Okay, predict x. All right, so now let's make it table form equals pd dot data frame. Here we're going to do country. Let me make sure I am getting it correct. Country named df country dot str dot capitalize. Okay, just to show the nations in capital letters, comma, actual equals log y, comma, predicted equals log y pred, log y pred, log y pred, comma, error percentage equals, error percentage equals 100 log y pred minus log y divided by log y. Okay, 100 times, I forgot the times. Okay, all right, so those are the ones. Let's display them here. All countries equals table form dot sort values with actual. Okay, now display round all in 2 decimal spaces. Okay, so this will show us the list of nations that we are making predictions with log model. Let's see now. All right, now you can see with log models the error numbers come down from 19,000 to 312.51% error in terms of Gambia. Actual is 0.99 billion. Now the predicted is 4.13 billion. So that is a 312.51% error. Suriname 1.5. These are log values, okay? Log values. 1.5, predicted 5.6, 460.02%. Here there is one, Afghanistan, 2.86 log billions in log values, predicted 1.99, which is 99.39. So you can see the magnitude of the prediction error has come down drastically, much more drastic. So you can see the validity of this model, log model, in comparison to the linear model. Okay, now for the overall validation, the important points are, these are the country differences, but mean value of the errors of prediction against actual, that is what we need to measure. For that we're going to do this. Okay, here r square equals r squared slash score log y comma log y pred. Okay, that will give us r square. Just let me print r squared log model is going to be around r square comma 3. Okay, that is r square. Now let's go to the, what is the next? Mean absolute error. MAE equals mean absolute error. Log y comma log y. Okay, mean absolute error is that. So print mean absolute error, MAE, comma round MAE times 3. Okay, that will give us mean absolute error. More important point is MAPE. Okay, MAPE equals mean absolute percentage error. Okay, that will be log y comma log y pred. Okay, log y pred times 100 times 100. That is more meaningful. Print mean absolute uh, absolute percentage error. MAPE is going to be percentage we will express in 2 decimals, round MAPE 2. Okay, so for the sake of just checking what percentage on average the model is off from the actual in its prediction. So let's run this and we'll see. Now you can see, look at that. There is day and night difference. Yeah, R squared matches. Now mean absolute error from thousands and thousands values, now it has come down to 0.982. Mean absolute percentage error, look at that. MAPE is 24.41% off. So the model is on average 24.41% off in predicting. That means 75.59% is correct. So which is pretty good. Pretty good job done by the model. Okay, so let me just close this by MSE, mean square error, equals mean squared error is log y comma log y pred. Okay, root mean squared error RMSE equals np dot square root MSE. Okay, print, let's print that. Print root mean squared error, errors in square roots. Okay, print root mean squared error is going to be round in 3 decimal places RMSE, comma 3. Okay, let's print this and look at the RMSE. Look at that. Root mean squared error is only 1.236. See, this is a dramatic improvement. So root mean percentage squared error. Let's look at root mean percentage squared error, RMPSE, which will give us in percentage terms root mean percentage squared error. How do we get that? np.sqrt np.mean log y minus log y pred divide by log y log y raised to the power 2 times 100% times 100. So this will give us root mean percent square error. Root mean percent square error. Print root mean percentage squared error. Squared SQUARED error. Okay, that will be round. We would like to show percentage in 2 decimals, right? Round RMPSE, comma 2. Okay, so let's look at this. Okay, look at that. Root mean percentage squared error is 47.47%. So root mean squared error is always looks at the distance, how much distant it is in making predictions. Okay, it gives us an idea of how much error the system typically makes in its predictions. With a higher weight given to larger errors. Larger errors are penalized with root mean square error. So from this measure as well, we can see the model is pretty good. Not the absolute percentage correct, but pretty good in making predictions. So today I explained to you the ins and outs of scikit-learn prediction, scikit-learn library's prediction capacity. Obviously, regression-based prediction is called supervised learning under the this is a supervised learning, instance-based learning. And there is another method. Usually, once people have become mastery of sklearn, people go on to deep learning, which does into the neural networks and all that. Deep learning is carried out by PyTorch method, but we are not there yet. We need to exhaust and understand the regression instance-based learning better. We need to practice this better before we go into the complications of neural networks. Linear regression, ordinary linear regression, is not so ordinary. It is so powerful. You can transform the models. You can deal with polynomials with the OLS. You can deal with reciprocals with OLS. You can deal with quadratic with OLS. So do not just give up on this and jump into deep learning PyTorch methods. Okay, this is the place where we should be focused and analyzing. This is rigorous scrutinizing of the predictive power of the model. This not only applies to the macroeconomics, this can apply to any situations. Say, for example, there are candidates running for office. If you want to predict the winning candidate, you can carry out regression analysis on the basis of various polls, various data up to that point. This model would be even more powerful if some wants to predict a nation's trajectory towards growth rate by looking at the time series data. So this is very powerful. Okay, so I hope I presented you a complete treatise of prediction using sklearn and also explained all the regression methods, diagnostics, the problems, and illustrated you how to improve by transformation of the methods, standardization of the data, all that. Please subscribe to my channel. This is the place for scientific discoveries, for economics as well as statistics, a complete learning space where you will learn all the methods. Subscribe to my channel. Stay with my channel. Let me know what area you want to focus more. Please comment. Subscribe to my channel. Bye-bye for now. Thank you for watching. Bye-bye.